We will derive the current equation of MOSFET in this lecture. We have already assumed that there is an inversion layer and the MOSFET is operating in triode region. As you can see, inversion layer is present in a trapezoidal manner. The capacitance per unit area for the oxide is equal to permittivity of the oxide divided by thickness of the oxide. Now, we will consider infinitely small strip of the gate at distance x from the source. The capacitance of this strip will be equal to capacitance per unit area multiplied by channel width into dx. Now we assume the effective voltage responsible for inducing the channel at point x is equal to overdrive voltage minus Vx, where Vx is the voltage in the channel at point x. So, the electronic charge which is present in the inversion layer in this extremely small strip of gate is equal to minus total capacitance multiplied by voltage. At point x, the electric field can be expressed as negative of gradient of potential. This electric field Ex causes the elementary electronic charge dq to drift toward the drain with the velocity dx by dt, where dx by dt is equal to negative of mobility of free electrons multiplied by strength of electric field, which can be written in terms of potential also. We know that the current is equal to dq by dt. Slightly modifying this equation, we can get current in terms of dq by dx into dx by dt. We have dq by dx to be equal to negative of capacitance per unit area multiplied by width of the channel into effective voltage at distance x. And we also have dx by dt. By putting the value of both these parameters, we will get current equal to even though we have calculated current at a single point, but as per Kirchhoff's current law, the current I must be constant throughout the channel. Thus, the current I must be equal to source to drain current. But we are interested in finding the current from drain to source rather than source to drain. Drain to source current is negative of source to drain current, which is equal to integrating on both sides, we will get therefore, drain to source current will be equal to this is the final equation of the drain to source current, which will be present in triode region. So, we have derived the equation for current for triode region, and we also know that for saturation region, the drain to source current becomes constant. Therefore, we can apply drain to source voltage difference is equal to overdrive voltage, which is equal to gate to source voltage minus threshold voltage. Putting the value of drain to source voltage in the above current equation, we can find the current equation for saturation region also. We got this current equation after assuming that at pinch of voltage, the drain to source current gets its maximum value and becomes constant. The product of mobility of charge carriers and capacitance per unit area is referred as process transconductance parameter. We have taken mobility of free electrons because we have considered n-channel MOSFET. Similarly, the ratio of channel width W to the channel length L is also known as aspect ratio of the MOSFET.